So let's look at Lesson 8. We're going to look at explosions and other problems. Now I started here with example 1, a 10 kilogram curling stone is sliding, and I've realized actually I already did this example with you in a previous set of notes, like a complete meathead. So we are going to, if you don't mind, scratch this question here. Scribble, 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 scribble. You did it already. Okay, let's move on to the next one, Mr. Dewick. A 5 kilogram puck, puck A, moving at 0.8 meters per second to the right, collides obliquely with an identical stationary puck, puck B. Puck B then moves off at 0.6 meters per second as shown. Hey, Mr. Dewick, this question looks familiar too. Yeah, it does. Mr. Dewick, I think we did this question already as well. Yeah, we did. We're going to scratch this one out? Well, I think you guys still need a bit more practice with oblique angled collisions. So here's what I'm going to do. We're going to cross out this 0.8. We're going to make it a 1.2 meters per second, which makes that a 1.2 meters per second. We're going to cross out the fact that it's an identical puck. Instead of making it 5 kilograms, we're going to make it 8 kilograms. And we're going to have puck B move off at, instead of 0.6, how about 0.45 meters per second? 0.45 meters per second. And just like that, it's a whole new question. Merry Christmas. Oh, and I guess if we're going to go sig figs, it should be 8.0 kilograms. So let's start. Is there a collision? This is a job for momentum. That's right. The first thing I'm going to write is the sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, what's moving? Mass A, mass B, or both? Looks like mass A. So it's going to be the momentum of mass A initial. Wham! They collide. Gee, I wonder if Gabby jumped. After the collision, what's moving? Mass A, mass B, or both? Both. So we have momentum A final. Oh, stuck together or separate? Separate. Momentum B final. So far, we haven't done anything different from linear momentum, but now we're going to dulp. We're going to carefully draw a picture. It looks like momentum A initial looks like that. And it's going to have a momentum of 1.2 times 5. It's going to be mass times velocity. I think its momentum ends up being 6 kilogram meters per second. And apparently that's going to equal mystery momentum A that I don't know, plus the final momentum of B, which is 8 times 0.45, and 3.6. Oh, and they gave me an angle. They told me that it was 29 degrees. You can see that on this side here, I have two lovely vectors. How can I add these together? I can draw them tip to tail, which I'm going to do up here. We're going to end up with mystery momentum A, final, plus 3.6. And I know that they add together to give me a horizontal resultant. I know that this is 6. Oh, they told me that this angle right here is 29 degrees. That means that this angle right here is 29 degrees. Because of that, there's an alternate interior angles if you want the official fancy smancy math rule. So this is 29 degrees. And yes, this is a job for the cosine law. We're going to get momentum of A final squared equals 6 squared plus 3.6 squared minus 2 times 6 times 3.6 cosine of 29. 6 squared plus 3.6 squared minus 2 times 6 times 3.6 times the cosine of 29. That's way too... Oh, square root, Mr. Dewick. Don't forget to square root your answer. The momentum of object A is 3.343. Of course, that's not what the question wanted me to find. The question wanted me to find final velocity, magnitude, and direction. How can I find velocity if I know the momentum? Divide by the mass. Final velocity is going to be, what was mass A? 5. So I'm going to go this divided by 5, and I get a lovely final velocity of 0.669 meters per second. Actually, that's only a final speed. They asked for a final velocity. I need a direction, and in fact, I'm pretty sure the direction I want is this angle here, theta. SOHCAHTOA? No. Ah, sine law. I'm kind of running out of room here, and I need to leave some room down here. So I'm going to scooch up here. I'm going to do the sine law in the top right corner. Not very organized, I know. The sine of the mystery angle divided by the side across from it equals the sine of the angle that I know divided by the side across from it, which was 3.343. I'm going to get sine theta equals 3.6 sine 29 divided by 3.343. And then inverse sine. 3.6 sine 29 divided by 3.343. Inverse sine, I get 31.5 degrees. At 31.5 degrees. What of what? North of east. And you know what? I really should have somewhere here drawn a little compass rose to make sure that I didn't do a sloppy mistake, because God knows I've done that very often. I think that's the answer. I'm doing this Friday night before I leave, and I haven't done this question before. If I made a mistake, and you know that I make mistakes all the time, I apologize, but your substitute teacher hopefully can correct it. But I think I'm right. Now we're going to add a part B. That's why I needed room down here. What's part B, you ask? What's part B, you ask? Oh, this isn't going to work. I'm doing this to an empty room. B. What is the change in kinetic energy? What's the change in kinetic energy? Well, change in anything is going to be final minus initial. Now, here's a nice thing. Kinetic energy is a scalar. I'm going to divide my screen into 3 little sections here. Kinetic energy initial. Before the collision, what was moving? Just mass A? It's going to be a half mass A VA squared. It's going to be a half times 5 times 1.2 squared. The amount of kinetic energy before the collision was 3.6 joules. After the collision, I have 2 things moving. My final kinetic energy after the collision is going to be a half mass A VA final squared plus a half mass B VB final squared. My final kinetic energy is going to be uh, 0.5 times 5 times, what was VA final? 0.669 squared plus 0.5 times 8 times 0.45 squared. How much kinetic energy do I have at the end? Hopefully I didn't gain kinetic energy. I hope. If I did, it's because I made up bad numbers. 0.5 times 5 times 0.669 squared plus 0.5 times 8 times 0.45 squared. I get 1.93 joules. What was the change in kinetic energy? 1.93 minus 3.6. I lost some kinetic energy. Minus 3.6. I lost 1.67 joules of kinetic energy. Now, that doesn't mean the law of conservation of energy was violated. Total energy is conserved. I didn't lose that energy from the system. I lost it from kinetic. You know what? That was the work done in deforming these masses when they crashed. It went into sound and heat. Kinetic energy is only conserved in what we called a perfectly elastic collision. That was that bizarre extra special case where kinetic energy was conserved, the masses were the same, and the angle that they rebounded off of each other was 90 degrees. Here, I lost 1.67 joules. Example 3 says, find the final velocity, magnitude, and direction of object B. Am I going to do that one? And then we have an explosion. Sure. Let's try this one. This is going to be really, really similar to the one we just did, I think. So, you know what? I'm going to go, let's get to an explosion. Example 4. A metal disc explodes. Boom! Did Yu-Chan jump? Into 3 pieces, which fly off in the same geometric plane. The first piece has a mass of 2.4 kilograms. It flies off due north. Oop, I see a compass. At 10 meters per second. The second piece has a mass of 2 kilograms and it flies east at 12.5 meters per second. What is the speed and direction of the third piece, which has a mass of 1.4 kilograms? Okay. This is a bit different because you can see there's 3 pieces. Mr. Dirk, now what? Hey, let's relax. Is there an explosion? This is a job for conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. Before the collision, what was moving? Mass 1, mass 2, or mass 3? And the answer is, before the collision, none. My initial momentum is 0, and that's going to equal the momentum of the first piece, and the momentum of the second piece, and the momentum of the third piece. Final, final, and final. What does the momentum of the first piece look like? It says it flew off due north. Oh, and it's 2.4 times 10. I can do that in my head. 24. Plus. The second piece flies off due east. And it has a mass of 2, and it flies off at 12.5. It flies off at 25 kilogram meters per second. It flies off with the momentum of 25. I can go 2 times 12.5 in my head as well. Plus, I don't know. Well, how do I add 2 vectors together? Draw them tip to tail, so it's going to look like this. 24, and almost exactly the same length, 25, a little bit longer. Now here's the key idea. What is my momentum supposed to add up to? Well, my final momentum has to add to 0 because my initial momentum added to 0. How can I show added to 0 in a vector triangle? that final vector must come back to where I started from, like we were doing a displacement of 0. This is the momentum of object number 3, final. Oh, and there's a lovely right angle. Now, if there wasn't a right angle, this would be a job for cosine law or sine law or holy smokes. Oh, and by the way, I like this question. I like this question. I like this question. I like this question. You can probably explain to my substitute teacher what that means. Yeah. I can use SOHCAHTOA. First of all, I can use Pythagoras. Momentum 3 final squared is going to be 25 squared plus 24 squared. No cosine law. The momentum of object 3 final is going to be 34.655. I'll carry a few extra sig figs. Of course, they didn't ask for the momentum. They wanted the velocity. How can I find the velocity of object 3? I guess I'm going to divide by the mass of object 3, which has a mass of 1.4. So if I take this, divide by 1.4, hey, now I got the speed, 24.8 meters per second. That's the speed at, now to make it a velocity. I think my vector is going this way, so I think there's my theta. I think it's going to be south of west. And I can go opposite, adjacent. I think I can say tan theta equals 24 over 25. So inverse tan of 24 over 25, and I get 43.8 degrees. I knew it would be close to 45 degrees, because if it was 24 and 25, it'd be exactly 45 degrees. So I'm expecting, 44 degrees. Okay. So if there's an explosion, you know that your initial momentum was 0, assuming the bomb wasn't moving before it blew up, which means your final momentum is 0, which means if you have 3 pieces, it better add to a vector triangle of 0. Basically, on a much larger scale, this is what the FBI or the RCMP or the CIA, when there's a bomb somewhere and they're trying to piece it together, they're collecting all of the pieces, not 3 pieces, many more. They're weighing them. And it's also trickier because I kept them all flying at a nice horizontal, the same geometric plane. I kept them all flying straight horizontally. In real life, that doesn't happen. So it's a much more complex problem, but the physics, the concept, still the same. And you can then work your way back and make a guess as to the mass of the original bomb and where the epicenter was. Hopefully, that skill becomes more and more useless as our world becomes more and more peaceful. That'd be great. Turn the page. Example 5, we have a roller coaster colliding. We've done one like this already. In fact, we did this question last lesson. I'm just noticing that it looks like when I typed this lesson up, I used a bunch of questions from my previous lesson and meant to change the numbers and forgot. Sorry. Anyways, we're going to skip example 5. We've looked at explosions. Here's a nasty scholarship question. I talked about this already, so you can skip it. We did this one, looked at this one last class. Really, you finished the unit. You can spend class working on the whole review. When we get back, I will give you take-home quiz number 2, and it will have lots of collisions at angles. You can expect to write your test on Monday, January, let me pause for 1 second while I go check my calendar, 14th. Now, I have one more important thing to tell you. This is your optional bonus homework for the Christmas break. Let me get it set up and I'll come right back. If you go to my website, pitmath.com, and you click on Physics 12, you will see the Physics 12 12 bonus video game. What's that, you ask? Well, click on it. This is going to give you up to 2 bonus marks on your momentum test. If you get a score of 15,000, you'll get 1 bonus mark on your next test. If you get a score of 25,000, you'll get 2 bonus marks on your next test. However, I won't let you get more than perfect on your test. Sorry. In order to prove what level you've reached when you play this game, you have to take a screenshot. If you don't know how to take a screenshot, click there for instructions, how to take a screenshot in Windows. Or you can Google, if you're using a Mac, how to take a screenshot for a Mac. Or another easier option would be to take a photo of your screen with your cell phone camera and email it to me. I'm assuming all of you at this point have a smartphone. But if you do email it to me, make certain in the email that you let me know who you are, because I can't recognize someone's cell phone number. What is the bonus video game? I'll let you click and find out. Well, have a very Merry Christmas, have a very, very Happy New Year and a good holiday. On Wednesday, you can bring homework from another class to work on. On Wednesday, you're going to watch a video called My Last Lecture about achieving your childhood dreams. Given the horrible and distressing events that occurred in the U.S. on Friday, perhaps we're thinking a little more deeper about life and future and our childhood dreams. Have a great break, folks.